You're welcome. You're welcome. So we are going to do some exercises. So the first one is this example. So you have a function. Maybe I'm going to write f of x is true that it's not written. It is written x of x. So to avoid repeating the same thing, it's better for me to take f of x equal to 1 if x is in Q. So the set of rational number 0 is otherwise. So when x does not belong to Q. So we want to show that f is not a Riemann integrable. F is not Riemann integrable. Now, and I hope that you have seen the concept of a Riemann integral function. And I hope that your professor defined something like the lower double sum and the upper double sums. I don't know if you got something like that. So I'm going to give a definition of what we mean by Riemann integrable. So it is like if you have your f, a function f from AB to R bounded and you have P, a partition of AB. So x naught, x1 up to this is just a partition of the interval AB. Now I'm going to define two concepts. The concept of lower double sum and upper double sum. Also, I'm going to define MI, which is the infimum of f of x with x between xi minus 1 and xi. I'm going to define capital MI, which is the supremum of fx, x between xi minus 1 and xi. I'm going also to define the step on the length of the interval xi minus 1 xi. So this is the length of the interval xi minus 1 xi. Now, what we call a lower double sum, lower double sum, namely LP of f. So it's the lower double sum of f over p. So it is defined as LP of f is equal to the sum of mi delta xi, I from 1 to n. So what I'm defining here is what we are going to use to show that that function is not Riemann integrable. Now the upper double sum u p f. So the upper double sum of f over p, namely UPF, is defined as UPF equal to the sum from I equal to 1 to n of ni delta I. So what you notice that for the lower double sum, we are using the infimum, and for the upper double sum, we are using the supremum. So we need to compute this lower double sum and the upper double sum to conclude about the notion of Riemann integrable function. Now, we are going to define also what we call the lower double integral and the upper double integral. The lower double integral depends on the lower double sum, and the upper double integral depends on the upper double sum. And if the lower double integral of f over the interval AB equal to the upper double integral of f over the interval AB, then f is Riemann integrable. But here, as f is not Riemann integrable, we are going to see that the lower double integral is different to the upper double integral. Now, what is the lower double integral? Lower doubles lower doubles integral of f over AB. So it is denoted like this. This is just the supremum of the lower double sum. P is a partition of AB. This is the lower double sum and the lower double integral. So it's the supremum of the lower double sum. So I can just put P under here. And the upper doubles integral of f over AB is defined as follows. Upper, and this is what is the infimum of the upper double sum. That is what we call the upper doubles integral. Now, as I said, to say that f is Riemann integrable, you have to show that these two quantities, so these two expressions, these two integrals are equal. So you have to show that the lower Darboux integral of f is equal to the upper Darboux integral of f. And I recall the definition of everything. Now, it was possible for me in the beginning to just start computing this, but now you know what is the lower double sum, right? You know what is the upper double sum, and you also know what is the lower double integral and what is the upper double integral. So what we need to do now is just to check. I hope that everything is clear for you for a moment. Are we together or you're not there?
Yes, yes, together.
Hmm?
Yes.
Okay. Now, so to do this, so you know that to compute the lower double integral and to compute the upper double integral, we need to compute LPF, which is the lower double sum, and UPF, which is the upper double sum. Now, what is the upper double sum? What is the lower double sum? So LPF, which was what equal to the sum of MI delta xi from 1 to n, and MI was the infimum of fx x between this and this. Now, just to recall what is f. F is equal to 1 if x is a irrational number, and 0 if x is an irrational number. Now, obviously, we see that the infimum of f is what? Is 0, right? Hmm? Can you see that the infimum? So
Yes.
the lowest value of f is 0. So
Yeah.
mi is just 0, right? So you conclude that LPF is equal to the sum of 0 times data xi, which is 0, right?
Yes.
Okay. Now, what is the upper double sum?
1.
This is the formula of the upper double sum. So if we take, for instance, just this is r. They put r. If we are just maybe if we decide to take maybe our x like the interval 0, 1. So we know that if this one does not work in 0, 1, it's not going to work on R. So just do a restriction. We just take it like this. Now it means that our interval AB is what? Is 0, 1. Or you can take any interval, you can take maybe any interval like AB. It doesn't matter. Any interval that you want in R. Now, oh, mi, as you said, is one. Mi, which is the supremum of fx, x between xi minus 1 and xi. So this function is very simple, so you don't need to compute. It will be 1. So the upper double sum, which is the sum from I equal of 1 times this. So it will be this one. And this is what? This is just of xi minus xi minus 1. And it is a heteroscopic sum. So what we are going to have is xn minus x naught. So it is b minus a. Since that xn is b is the highest value of the interval and is the upper bound of the interval ab, and x naught is the lower bound. So this is our upper double sum. So now we have our lower double sum. We have our upper double sum. So we can compute now our lower double integral. Now, what is the lower double integral? As we know, it is the infimum of, it is the supremum, sorry, don't forget the formula. It is the supremum of what? Of the lower double sum, which is 0, right? It is 0 because the lower double sum is
Yes.
0. And what is the upper double integral? The upper double integral is the infimum of the upper double sum. And we found that this one was a constant. So it will be the infimum of a constant, which is a constant. Mm, yeah. So the lower double integral of f over ab is different to the upper double integral of f over the interval ab. Then f is not Riemann integrable on ab. Then f is not also Riemann integrable on r. So I hope that everything is clear here. Okay, nice. So as everything is clear, now What was the next question? Okay, the next question is, so yeah, so we answer just the question like that. A norm, when a norm is associated to an inner product. So this question is very easy. Of course, when you have a norm, we know that when you have maybe I don't know a norm space, uh yeah, yeah, it's true that maybe I wanted to say something. When you have a inner product space, you can define a norm because the norm may be of X. If you have maybe the norm, it's not the same thing. Maybe this is the case that we are working on a norm space. So it's not automatically true that when you have a norm, you are going to have an inner product. But when we are going to do inner products, inner you call it prohibition spaces, so or inner product space. When you are going to do inner product spaces, or when you are going to do Hilbert spaces, you will notice that when you have an inner product, you can define a a norm, but it's not always sure that when you have a norm that you can define an inner product. Now, what is the condition when you have a norm you can define an inner product? Um, I'm just going to write something simple. Obviously, when you have a norm space, and if the parallelogram law is satisfied, then you can define an inner product. So a norm like this on a vector space X is associated to an inner product if and only if the parallelogram, if and only if the parallelogram law is satisfied. Okay. So what is the parallelogram law? It means that if you have x and y, two elements of x, the norm of x plus y square plus the norm of x minus y square equal to 2 norm of x plus 2 norm of y square. So the norm of x plus 1 over square over 2 uh, plus the norm of x minus y square equal to 2 norm of x square plus 2 norm of y square. This is what we call the parallelogram law. So if this is satisfied, then you can conclude that a norm is associated to an inner product. That is all. And we used to define it like this. Is the inner product or like this. That is the condition. I hope that's good for you. So you just have to memorize it. Is it good for you? Are you there?
Yes.
Oh, okay. I was thinking that you left.
No.
Okay. Next one. It is written exercise 6. Exercise 6. So you have x, which is given by the set of continuous function from minus pi to pi in R involved with a uniform norm. Now, the identity defined from x to x. I hope that you know very well the identity function. It means that the image, if you take an element, the image of the element is still the same element. That is what we call identity. So it's x. Is the identity compact? So we are just going to check the hypothesis of the Ascoli-Azela theorem. I hope that you know the Ascoli-Azela theorem. I hope that you did it. Did you do Ascoli-Azela theorem?
Yes, we did it.
Okay, nice. So the first thing that we are going to check here is that if the identity is, if we take maybe, of course, the answer is no. And we are going to take a counterexample. So to take a counterexample, we are going to take a sequence of functions. So it was given in your notebook. So if you take fn of x, let's consider the following sequence of functions. Fn of x equal to sine of nx defined on minus pi pi. Okay, so the first thing we are going to check the boundness. So for all x in minus pi pi, and we know that, what do we have? The absolute value of fn of x equal to the absolute value of sine of nx. So, and this is always less than 1. So this implies that the norm of fn is less than 1. And we know that if the norm of fn is bounded, or if it is finite, if the norm of fn is finite, then fn is bounded. So the first thing is satisfied. Now we are going to check the equicontinuity. Equicontinuity. So is fn equicontinuous? So we are going to check it if fn is continuous, if xn is equicontinuous. Now, what is true that we can see is that fn, so the sequence of function fn is not equicontinuous at x equal to 0. We can prove it. If we take a small h, if we take a small h, sine of n of x plus h minus sine of ns nxh of sine of nx is this one. We can use the mean value theorem. So this is equal to something like nh cosine of nx. You can, so if you have your function maybe like this is your function. Of course, this is, let me write the truth. So this is equal to f prime of ac times nx plus h minus nx, and c belongs to the interval, this interval. Now, what is your f? Yeah, f is, sorry. What am I writing like that? This is x plus h, and here it is x plus h minus x. This is the mean value theorem. Maybe we have our x, we have this equal to sine of nx. This function is differentiable. Now, what is f prime of nx? H is equal to n cosine of nx. That is it. Now, by the mean value theorem, we have what? Fn of x plus h minus fn of x equal to f prime of c times x as x plus h minus x. And c is between x and x plus h. This is just for a small. This is just for a small h, and we can also take this c like h. So since that h is too small, we can take it like h, and this is what is just n cosine of hx. Here is h, so we have nh cosine hx. Now, if we taking x equal to 0, we have sine of nh minus sine of 0 equal to sine of nh. By choosing h equal to pi over 2n, what do we have? We have sine of nh equal to 1, because this one is 0. And if we take h equal to pi over 2n, we are going to have sine over pi over 2, which is 1. So this one equal to 1. And when n tends to plus infinity, when n tends to plus infinity has when n tends to plus infinity, h tends to 0. H tends to 0. And if you come back here, what are you going to have? We are going to have sine of nh equal to 0, which is different to 1. Then fn of x is not equicontinuous. So the problem was here. So we wanted to show that this function is not, this sequence of function is not equicontinuous. And we notice that this sequence of function is not equicontinuous at x equal to 0. So, and we want to show it. You can consider maybe by contradiction that it is equicontinuous at 0. So it means that for a small h, we have this. And this comes from the mean value theorem that I was trying to explain here. That is what I was trying to explain here. Now, we found out that when you have this, when you have this, uh, when you have this, if you take x equal to 0, if you take x equal to 0 and you replace here, you are going to have this result. And also, if you choose a particular, you are going to have 1. And if you choose a particular value of n, of h, you notice that when n tends to plus infinity, h tends to 0. And when h tends to 0, you come and you replace again back here. But you are going to notice that we have 0 instead of 1. So it means that our function is not equicontinuous at 0. And if it's not equicontinuous at 0, it means that even in the whole domain, it's not equicontinuous. So has the equicontinuous is not validated, then IG, the identity is not compact. So the boundedness was true. But after the boundedness, we were supposed also to check the equicontinuity. And we noticed that one of the hypotheses is not verified. And this hypothesis is the equicontinuity. Yeah, I understand maybe it's not very easy maybe to understand it. But to check the equicontinuity, you can find the definition of the equicontinuity maybe on your notebook. So you know that a family of function f is equicontinuous if for all x and y in x, and there exists, and for epsilon positive, such that the absolute value of this less than this imply that the absolute value of this minus this is less than epsilon for all f in the family of function. That's the definition of equicontinuity. But in our case, it's not satisfied. So you just have to try to understand how the equicontinuity works. So the next one is it's a theorem. The theorem said every linear operator, every linear operator is every linear operator of finite dimensional spaces is bounded. So if we take let x and y be two norms vector space, with dimension of x equal to n, the final dimension. And let t from x to y a linear operator. T is a linear operator. Can you hear me again?
Yes, yes.
Okay. And T is a linear operator. So we want to show that T is bounded. So we want to show that T is bounded. The first thing that you have to understand is that when it is said that we have a finite dimensional space, it means that you can define a basis in that space. So if the dimension of the space is n, it means that a basis of x has n vector. So let b equal to e1, e2 up to en, a basis of x. So x is finite dimension and the dimension is n. So that is why I take a basis of n vector. Now, if I take an element in x, let x in x. X can be written like what? x1, e1 plus x2, e2 up to xn, en. So it can be written like the sum of xi, ei, I from 1 to n. That is it. Now, what is tx? Tx is t of the sum from I equal to 1 to n of xi, ei, which is equal to the sum of I to n of xi, t of xi. Now, what is the norm of this? The norm of tx this y is equal to the norm of this. So this is how this is less than the sum from I to n of the absolute value of xi times the norm of txi. Yeah, right? I hope that you understand. And this is less than a constant m times this sum. And this, we are in finite dimension. We are in finite dimension. So we know that in finite dimension, all the norms are equivalent. So this is less than something like m times a k norm of x, since that we're in finite dimension. So you can take everything like C norm of x. Then T is continuous. Yeah, I think that maybe you are surprised. That is that in finite dimension, every continuous linear operator is bounded. So T is bounded. Every continuous linear operator is bounded. Maybe if you have any question, you can ask. And also, you can also say it like this: the norm of T is less than C, so which is still bounded. So this one, I think that the proof of this one is very easy to understand. The first thing, the origin that you have to know here is that you have to use the concept of a basis, and it's done. Do you have any question here? Okay, so now we are going to do the last question of the day. So given a sequence of function fn of x equal to 1 over x plus x power n, x in 0, 1. So we would like to apply the Lebesgue convergence theorem. So let us apply the Lebesgue dominated convergence theorem. So what I'm going to do before applying it, I'm going to state it. Okay. Lebesgue dominated convergence theorem. Lebesgue dominated convergence theorem. Now, if you have a sequence, so let Fk a sequence of functions defined from Rd to negative infinity plus infinity. So be a sequence of measurable function suppose. So before continuing, I would like just to say that the goal of the Lebesgue dominated convergence theorem is to compute the limit of a sequence. So or to so we want to compute maybe the limit of the integral of a sequence, and we want to switch the position of the integral and the limit. So you want to make the limit inside the integral, and there is a condition that must be satisfied. So suppose that there exists a measurable function there exists a measurable function f from Rg to minus infinity plus infinity such that the sequence of measurable function converge to the measurable function f almost everywhere. The second is there exists a summable function j from Rg to 0 plus infinity. So summable function is just an integrable function. So an L1 function. So if that is summable function. Such that the, the absolute value of this is less than gx. So the absolute value of the sequence fk is less than gx for almost every x in Rg. Then, so when these two hypotheses are satisfied, then the limit of the integral of fn dx when n tends to plus infinity is still the integral of fx dx. So it means that you can switch the limit with the integral. So it is like this. So the limit of the integral of the limit of fn dx. And this limit is this. So if you're asked to compute maybe a limit of a function, and the function is very difficult, you can find maybe a sequence or function which is going to satisfy everything which is here, and you're going to compute the integral as well. So this is the Lebesgue integral. This is the Lebesgue dominated convergence theorem. Now, we are going to apply the Lebesgue dominated convergence theorem here to this function. This is our function or sequence x in 0, 1. What we know is that the first is that fn is a sequence of measurable function. Why fn is a sequence of measurable function? Fn is continuous, and when you're continuous, you're measurable. But the converse is not true. Fn is a sequence of measurable functions. Now, what is the limit of Fn? According to you, what is the limit of Fn? Is 1 if x equal to 0, and 0 if x is different to 0. I hope you understand. If I take x equal to 0,
Yes.
I'm going to have one over 1 plus 0, which is 1.
Yes.
But if x is different to 0, as long as x is between 0 and 1, it means that x power n is going to vanish to 0. So you're going to have, oh, am I serious? If x is equal to 0 to 0, no. This limit is always 1. You cannot have 0 because x is between 0 and 1. Sorry. What I'm saying is that x is between 0 and 1. So it means that the limit of x power n when n tends to plus infinity is 0. Right? But the problem is that, let me check again. If x equal to 1, what do we have? Do we have 0 if x equal to 1? I don't know if you understand. It's 1 over 2 if x equal to 1. It is 1 if x is between 0 and 1. Yeah, this one is true. So this one is what is our f of x. If x equal to 0, we are going to have 1 over 1, which is 1. If x equal to 1, we are going to have 1 over 1 plus 1, which is 1 over 2. Now, if we remove 1, we are going to, this one is going to be 0. I hope that you understand. This is the limit. Now, what do we know? This one is this. This is always less than 1. True or false?
True.
And 1 is measured, and this is summable in 0, 1. Then we can apply now our Lebesgue dominated convergence theorem because everything is satisfied. You have our f because they see that the exists f is the limit, as you can see. Now, so by Lebesgue dominated convergence theorem, the integral, so the limit of fn of x dx has n tend to plus infinity is equal to the integral of the limit. So this means that the limit of the integral of 1 over x power n dx when n tends to plus infinity is equal to the integral from 0 to 1 of f of x dx. This is what? This is the integral of 1 dx, which is equal to 1. So the limit of this is 1. So we are done. I hope that you have understood everything. If you still have a problem with this limit, please let me know, because you have to check everything here when you're computing this limit. That is what we call the pointwise limit. You have to check it very well. You have to be very careful. And this pointwise limit is not continuous. So it means that this sequence of function is not uniform convergence. So this sequence does not converge uniformly. So we cannot have uniform convergence here,
Okay.
because this pointwise limit, this pointwise limit is not continuous.
Okay.
I hope that you understood the goal of the Lebesgue dominated convergence theorem. It's the same thing like the bipole theorem or the monotone convergence theorem. Do you know the bipole theorem?
Yes.
Nice. So the monotone convergence theorem or the bipole theorem. Okay, we are going to stop here. Maybe on Monday or on Sunday if people are available. Search that. Maybe by learning many people. I'm not going to do the same thing every time. But this is like people don't have problems. So no matter. Maybe on Monday you can still do it. We are going to do non-speaker on Monday. So thank you.